Hello everyone, I am welcoming you all once again to this channel. Today I am going to create the heterostructure of SRTiO3 and LaAlO3 using our VESTA software. First I am going to open the structures using our VESTA software. So here I am opening both of these CIF files, and this is the SRTiO3 CIF file and this is the LaAlO3 CIF file, and first step is to export these files into the VASP format. So here simply I am saving it into the Cartesian coordinate, and the same operation here we can do for the LaAlO3 Cartesian coordinate. Okay, done. Now let's open the file that we have saved now. So here I am opening this SRTiO3 VASP file, and here you can see also you can see, as the name suggests, that this SRTiO3 should have one SR atom, one Ti atom and 3 oxygen atoms. This we can also see from this file, VASP file that we have saved now. You see in the postcard we have one SR atom, one Ti atom and 3 oxygen atoms. But here instead we are seeing a lot of atoms. So to control and to check that, to see that exact number of atoms, we can go and we can do this option, do not search atoms beyond the boundary, and here also do not search atoms beyond boundary. Apply. Okay. So now here you can see that instead of large number of atoms we are seeing some of them, but still if you want to see the exact number of atoms that we have seen in our postcard file, for that we need to change this boundary. So here I am changing this boundary value from 1 to 0.99 and apply. Then okay, now you can see that we are only left with the 5 atoms, and this one is our SR, this is our titanium, and these 3 red color atoms are oxygen. In the summary we can see that the lattice parameter value for this SRTiO3 is 3.91270 angstrom, and A, B, C values are same, and also this alpha, beta, gamma values are equal to 90 degree, and this is the cubic unit cell of this SRTiO3 structure. Okay, similar thing we can also do for the LaAlO3. First is to do the bond control. So here this do not search atoms beyond the boundary. Apply. Okay, then we can go to this boundary thing, and here also we will do this change. Apply. Okay, now we are seeing here also 5 atoms, and this green color atom is our lanthanum, and this is our aluminium, and these 3 red color atoms are oxygen. And in the summary here we can see that the lattice parameter for this structure is 3.78295, and this ABC is also same, and alpha, beta, gamma is equal to 90 degree. So that means this is also the cubic structure of this LaAlO3. And if we will compare the lattice parameter value for this SRTiO3 and this LaAlO3, the value for SRTiO3 is 0.91 and for this one is 0.78. That means they don't have that much difference, which will create the lattice mismatch further when we will create the heterostructure. So without doing any further operation, we can simply go ahead with our heterostructure formation. So here I am going to open again the same SRTiO3 VASP file. Open it, and this is the file that we have opened now. Here, to create the heterostructure, we should open both of these files together. So I am going to this edit. Here in the edit data, in the fetch, we can import the second structure. So the second structure is LaAlO3 VASP, and I am opening it now. And here, without making any change, I am going to click on this apply button, then okay, to see that what is happening. Now you can see that we have both the structures merged together because we have not given any separation distance between them. So now again go and do the same thing. So the second structure I want to be separated at this value, and click on apply. Okay, along the z axis we have given the separation value. Okay, and now you can see that both of these structures are now separated at certain distance. And first we will remove these bonds to see how much is the separation value. Remove it, this value, do not search. Okay, apply. Okay, and as you have seen, we did this bond changes for the SRTiO3 one, and similar way we will do for this LaAlO3, and here also the same thing we are going to perform, and here also apply. Now the extra bonds that were present, like the apart from the boundary, is now deleted. So here if we will measure the distance between both of these structure, this distance is now 3.0873. As we know that while creating the heterostructure, both of these structures should align at a certain distance, at a certain separated distance. So that distance can lie from 2.5 to 3.5 angstrom, and in our case this distance is 3.087 angstrom, so which is also reasonable. So now let's go ahead with the heterostructure formation. So here as we can see that these are nothing but the unit cell structure that we are seeing in the page now. But to create the heterostructure we should have a bigger file or bigger structure. That means we need to have a supercell. So here we can create the supercell of the structure of SRTiO3, and here we have chosen this SRTiO3. Let's go to transform and let's elongate this structure along the x direction twice. Yes. Okay, apply. Now you see that this structure is now elongated along the x direction. Similar way we can choose the second structure and do the transform operation here. Instead of 1 I am writing 2. Then okay, yes, search atoms. Okay, apply. So now you can see that both of these structures are elongated. And now to create the heterostructure, what we need to do, we need to also take care about the periodicity. So to check that, I am going to align this heterostructure along the AB plane. So so this is, we are seeing the heterostructure from the AB plane, and you can see that the atomic coordinates are present here, are repeating here also, and the atomic coordinates present on this side is also repeating along this side. So we should remove these extra atoms, so otherwise it will repeatedly show in our input file. And similar way we can delete the upper layer atoms. Delete. Let's check some bonds we are left with. Let's delete those as well. Delete, and here is also another delete. So now you can see that this is our heterostructure that has been created using this VESTA software. Let's go and export both of these files together. So here I am first going to export this as the VASP format, and no, we are going to save it as the heterostructure. So hetero I have given the name, and here we can save it to the Cartesian coordinate. Instead of the output of the current unit cell, we should choose the option output coordinates of all the displayed atoms. Then click on OK. And also we can save the same thing into the XYZ format, and here I am writing hetero XYZ save. No. Okay, so let's go. Let me close this and let's go and open this hetero VASP. in the text file. So I am opening it with the text editor, and this is our VASP. And similar way we can export our XYZ file. Open it with the text format. Open. So this is, now let's compare. So in the left side we have the VASP format, and the right side we have the XYZ format. And here what we have seen, that we have 4 SR coordinate and and here also we have 4 SR atoms coordinate, then 2 TI atoms, then here 2 coordinates for the 2 titanium atoms, then we have 18 oxygen atoms. But here we have 1 2 3 4 5 6 7 8 oxygen atoms, and the remaining I think 10 must be there. 1 2 3 4 5 6 7 8 9 10, yes. So 10 atoms are here. Let's take it to the near to the, so here I am taking the rest oxygen atoms and pasting over here. Save the file. And here we have 18 oxygen atoms and 2 lanthanum, here also the same, and 4 aluminum, and also here also the 4 same. And if you will compare the Cartesian coordinates for both of these files, we have the same Cartesian coordinates for all these atoms. And now let's go and open the heterostructure which we have saved in the VASP format here. So I am going to the open to the hetero VASP file here. So now you see what happened. So here that both some atoms are merged together. And why it is happening? Because we have not maintained the Z coordinate for both of these structure. Because while creating the heterostructure, we typically provide the vacuum along the Z direction. So here we need to prove the vacuum value. Suppose I want to provide a vacuum of 20 angstrom, so instead of 3 I can simply write to 23. And as all this structure is saved in the Cartesian file, it will not impact to any of the coordinate, rather it will rearrange. So let's save this and again go to the VESTA software and open it. And here I am opening the heterovasp file again. Yes, now you see that the heterostructure of this SRTiO3 and the LaAlO3 is now created. And if you want to remove that extra bonds, simply you can go and do not search atoms beyond the boundary. Okay, apply. Okay, now you see that this is the heterostructure that has been formed using our VESTA software. And here you might see some kind of bond is not forming between this oxygen and this aluminium, which is having a bond length of 2.15, and here on this side it is having the bond length of 1.89. And why they are not forming any bond? Because this structure is aligned along with the lattice parameter value of this SRTiO3, because it was having a higher value than the previous than this one. And as per the bond criteria that has been maintained using this VESTA, we are not seeing any bond. But if you want, you can also add the bond, like here suppose the max length is this much or something, so you can simply increase this max length. Suppose I am increasing this to 2.2 or something. Click on apply. Yeah, you see that you have got the bond that was not visible earlier. Okay, so this is how you can edit, like you can edit and control your visualization using the VESTA software. So this is how we have created the heterostructure. Now after optimizing this heterostructure, the all these atoms can have their exact and correct coordinates within the same box. Okay, so this much for today's video, and thank you all, and bye bye.